Good morning, everyone, and welcome to today's second session of the Ambassador's Water Experts Program on the hydrogeology of the carbonate region of northern Belize. I'm excited to see some familiar names joining us again today, but for those of you who were not able to join our first session, my name is Elizabeth Goffey, and I'm a project manager with the U.S. Department of the Interior's International Technical Assistance Program. The Ambassador's Water Experts Program, or AWEP for short, is a partnership between my office and the U.S. State Department to provide short-term technical assistance on water to our foreign government partners around the world. We are incredibly grateful to the State Department in Washington and in Belize for their support of today's session. Before we get started, a few housekeeping reminders. The session is being recorded and will be uploaded to our YouTube channel. We will share both the slides and the recording link for your future reference. For audio quality purposes, we ask that all participants please stay on mute unless they are asking questions. We have also extended this session to 2 full hours to ensure that we have time for questions at the end. So please feel free to use the chat to both introduce yourself and share any questions that you might have. With that, I believe we're ready to hand things over to our experts for today. So Anne and Phil, take it away.
Thank you, Elizabeth, and welcome everyone. Thank you. That was a hard one, and we appreciate your effort to join us today. It's so much better with you here. My name is Anne Murray. I'm here with my partner, Phil Martin. We're Wellspring Water Solutions, and we are so pleased to be here to present this second webinar in the training series. Wanted to talk to you a little bit about the purpose and objective, just kind of recenter ourselves on this series. So the purpose is to provide the hydrology unit and others of you who are participating with a basic to mid-level hydrogeologic concept. This information will better equip you and give you the tools needed to manage groundwater more effectively. The area of focus is the Corzal Basin that is underlain by the Yucatan Aquifer. There's little published information on this aquifer in northern Belize. Much of the data is from work conducted in Mexico. But what we do know is there appears to be sufficient water to meet current needs, and that the quality of water discharged back into the environment is generally poor. There is a tremendous opportunity ahead to better understand and manage aquifer resources. We offer an overview of tools, methodologies, and actionable steps in this presentation that we hope you'll find useful. In webinar 1, we covered the basics of geology and hydrogeology. We discovered and talked about the geology of Belize, and in general, the types of aquifers, aquifer properties, and groundwater concepts. In this second webinar, we'll discuss groundwater assessment, availability, water balance, and vulnerability. These webinars are in preparation for webinar 3 that will focus on planning and implementing groundwater monitoring networks. As Belize grows its population and industries, there'll be additional stress placed on water resources in comparison to pre-development conditions. The key to ensuring ample and clean water for people and the environment is to strengthen stakeholder participation to support resource management. And that means conserving, protecting, and ensuring resource sustainability well into the future. I want to turn it over to Phil so he can tell us a little bit about the regional setting.
Thank you, Anne. Phil Martin here, also a hydrogeologist in the second half of Wellspring Water Solutions, and I'm also very pleased to have everyone here today for this presentation. Before I begin, I do have to point out an unfortunate circumstance here. It turns out that Wednesday afternoons are when the guys who come to cut my lawn will be showing up, and probably sometime during this 2-hour period. So apologies beforehand for the noise. Obviously, when I'm not speaking, I'll have my thing on mute, but it's almost inevitable that there'll be some times when I'm trying to talk and you're going to hear some noise in the background. So sorry about that. I should have canceled them, but there wasn't time to get that done when I realized. And so they'll be here, but I'll have a nice cut lawn after the fact. Okay. We're going to start out here today with a little bit of a review about the geologic setting and the overall aquifer system. You probably remember these two graphics from webinar 1. And what we have here is The Corizal Basin of northern Belize, it's an extension of the Yucatan platform that comes down from the Yucatan Peninsula. And it's comprised of a thick sequence of what's referred to as non-clastic sediments deposited during a 50 million year history of tectonic uplift, erosion, faulting, and shallow sea transgressions and regressions. It's characterized by a very thick sequence of dolomites and more recent pure limestones. You probably remember us talking about pure limestones that have been deposited mainly from marine origin. It's noteworthy that the rivers north of the Maya Mountains flow in essentially straight courses and are apparently dominated by the major faults and fractures in this area. And I think you recall also, we had some discussion about that faulting. It's fairly extensive. And those could play a potentially important role going forward when you get into monitoring and characterizing. There'll be some more of that in the third webinar. So the Maya Mountains to the south in central Belize are over 900 meters high in places. And these are comprised of Carboniferous or late Paleozoic metasediments. Remember the metamorphic rocks and volcanics that are there with some intrusive coming in. And it represents a big chunk of poorly defined Mayan crust that tilts westward over towards Guatemala. The overall stratigraphy of Belize is actually rather poorly or incompletely defined, due partially because there's a lack of good outcrop exposures, especially when we're talking about the Corizal Basin in northern Belize. And this is true because of the lack of outcrops, and also because there's very little in the way of fossil controls, which can help to give a better picture of the stratigraphy. So in general, the Corizal Basin can be described as carbonate dominated, which we know it's limestones and dolomites down deeper. And the Belize Basin to the south sees much more clastic input in large parts of the section there. So up in the Corizal Basin, the karst landscape comprises a large part of the country and certainly the entirety of the Corizal Basin, essentially, from the coast down to the Maya Mountains, characterized by the springs, caves, sinkholes, and aquifer systems formed by the dissolution of the carbonate rocks. And we talked a lot about that last time. To the right is a map that presents the full extent of the Yucatan Peninsula and the regional karst aquifer that underlies the northern portion of Belize. This map also shows the topography and indicates the generally low elevation of the Corizal Basin. The northern portion of the Yucatan platform itself is likely significantly impacted by the Chicxulub impact crater, which, as you will recall from the first webinar, was the event at the end of the Cretaceous about 66 million years ago that ended the dinosaurs and significantly changed life on Earth coming forward from that event. Its impact was just offshore to the northwest of the town of Merida that's shown on the map there up at the north. So if we can go on to the next slide there, please, Anne. So looking at the features of the karst limestone, and this again is going to be another review from the first webinar. So karst aquifers, what are they and what's important to know about them? Recall that these aquifers are particularly difficult to assess and characterize due to the many solution features and extreme heterogeneity and anisotropy, and I hope you remember those terms. As per the graphic here, there's both major and minor scale solution features which allow for both vertical and horizontal movement of water that can be very, very difficult to characterize and predict. And note that not all of the features that are on this graphic here actually exist and are applied to the Corizal Basin. But what is true is that the conduits and caves that are depicted are very numerous in the Yucatan Aquifer and the Corizal Basin and will impact water flow on all scales. Now, just briefly to look at a couple of the terms here that do apply, the point infiltration would be things like the cenotes or open lagoons where water could directly be in contact with the lower portions of the limestone. Diffuse infiltration, which is the primary way in which precipitation water will get into the aquifer itself. We do have something called the epikarst zone here depicted, and this does exist in the Yucatan in the Corizal Basin as well. And this is an area above the water table, which, by the way, is depicted as that dashed line at some depth. And you can see where it's saturated, where the conduits term is, where it's dark blue, and then above that where it's more or less dry or water is percolating through, but it's not fully saturated. Well, epikarst zone which really means skin of the karst. It's kind of like the upper portion of it. Because it's pretty porous and it's more weathered and kind of, if you want to use the term rotten limestone, it can provide some shorter term storage of infiltrating precipitation. And it can also create some perched aquifers in limited areas, which you may encounter with monitoring wells or with other activities that you do, whether with geophysics and that type of thing in the future. So if we go on to the next slide, we're going to take a look at some of the hydraulic properties of the karst aquifer system. Now, I love this photograph. I have to say, I just cracked up when I saw this because it's perfect. This is what I refer to as flow that's being measured in tourists per minute. Now, this photo was taken in a cave in Belize, and it's these kind of features that are going to make your attempts at reliable characterization of the aquifer so difficult. But I do have to say that the tubing looks like it could be a lot of fun. It'd be something, perhaps some of you have even done this type of tubing in the caves in Belize. But on a serious side, while there is a flow direction that's obvious in this photograph, which appears to be okay from left to right, where does it go next? How would you predict where the water would be going? Look at the solutions that are going off to the sides here. Are they additional conduits that extend for feet or meters or miles, or are they just dead ends? It's really, really difficult to tell. And so any point source of data is good for that point, and that's really about all. Well, let's take a minute and go through the ramifications of the bulleted items that we have here. And you'll recall variability extreme. And this would be in the hydraulic conductivity, transmissivity, and storativity. And that variability makes it almost impossible to derive useful values that can be applied to anything on less than a very large bulk scale of the aquifer, especially with respect to developing predictive assessments with any level of confidence. Another important factor is that with karstic limestone, there may be areas where the rock mass is essentially unimpacted by solution features, and especially at some depth, and will thus exhibit really negligible hydraulic conductivity and storage. And because of that minimal saturation, essentially no transmissivity, there can also be significant differences in the vertical versus horizontal parameter values. And these values can range over several orders of magnitude. And we're going to have an example of that in an upcoming slide. And it's possible that there's in some places, actually little intergranular movement of water due to the overriding impacts of the solution conduits or the fact that the matrix itself in deeper settings where it's not impacted by solution simply is relatively impermeable. Now, the complex flow pathways within the aquifer, while generally assumed to reflect the gradient from higher elevations towards the ocean, it can be expected to be highly complex as well as just the other parameters, and extremely difficult to map out. Now, we do know that some of these have been mapped via cave diving teams where they've been flooded, and they can extend for miles. And in fact, some of the largest cavern systems in the world exist in the Yucatan aquifer. Note that there are some indications also in the literature that there could be some level of transboundary flow coming in from the Mexican portion of the Yucatan Peninsula into Belize, and that this may be occurring. It's something that should be potentially a target of monitoring efforts going forward. Don't forget also about the faulting that's in the Corazal Basin that we mentioned just a minute ago. This was noted in the first webinar, and these faults, which are fairly extensive and they tend to run from southwest to northeasterly, they can act as either significant conduits of water running over very long distances, or they can alternatively act as essentially barriers to flow. It really depends on the specifics of the geology and what has happened along that fault plane itself, whether the rocks there have been gouged up and broken to pieces and then kind of re-cemented, or whether they're actually just more of an open kind of fractured rock type thing that can transmit water. Unknowns again. Scaling effects, and we'll be talking about this quite a bit today. This is meaning that how broadly or closely you make your assessments of the aquifer parameters is going to impact the results you get. And this has to be considered in any attempt to develop a generalized characterization of the aquifer parameters and flow pathways. As I said, there'll be more on this coming up. Vulnerability to surface-derived contamination. Because of the superficial weathering and widespread diffuse flow into the aquifer in the epikarstic zone, the entire system itself is potentially extremely vulnerable to any surface-derived pollution from a variety of sources. And these can be things like sanitary discharges, agricultural activities, using pesticides and fertilizers on the ground, commercial and industrial activities where they're taking water and treating it for some use and then putting it back, discharging it back into the aquifer. Again, there'll be more discussion of this a little bit later. So with that, if we can move on to the next one, Ann. The aerial distribution of hydraulic properties, and this is what we get into when we talk about the scaling issues and the fact that it's difficult to rely on any single value to get a good idea of what's actually going on a larger scale within the aquifer. Now, what we have here, because of the solution features and the unpredictable nature of the flow pathways, the scale at which you assess a specific area can result in widely different values and widely different results. This applies to the hydraulic properties in particular, but also to the solution features themselves, as you would rationally figure would follow from that. So what we have in this photograph here is from a Google Earth graphic that was developed for our Bahamas project last year. And I'll note that, by the way, that the aquifer that's at work here that we were studying in the Bahamas is almost identical to the Yucatan aquifer. It's not the same one, but it could be its brother, really. It's very, very similar. A lot of solution features, very similar mineralogy. So it's very close analog to what we have in the Corazal Basin with the Yucatan aquifer. Now, I want to point out some of the values that are here, and this is measuring specific capacities along this roadway in Grand Bahama, where a bunch of monitor wells were drilled for a number of purposes, but not the least of which was to try to make evaluations of this parameter. Specific capacity is a measure of how much water can be yielded from a well with a given amount of drawdown when the well has reached an equilibrium situation where the water table is not changing as it's being pumped. So it's measured in the typical unit of gallons per minute per foot of drawdown at equilibrium. So what we have here, you look at these numbers. We have two that were tested at 3,500 gallons per minute per foot of drawdown. In other words, you pump the well, you're pumping it, a huge amount of flow and only getting a foot of drawdown. But the other range of values is much, much different. Starting from the south and going to the northeast here, 700, 189, one next to that 3,500, I mean, right next to it, short distance away, 10, then 64, 14, some other lower numbers, and then 73 up in the upper right. So you can readily see that we've got as much as 3 orders of magnitude in this value, the specific parameter, over a very limited geologic area. So if you were to pick any one of these values presented, it would only be telling you what's happening at that one spot. And it doesn't really give you a good idea of how the aquifer as a whole is going to respond to any kind of pumping stress or any type of activities regarding water table changes and things of that nature. So similarly, if you were to average a few of these, you're likely to have the same problem. So the scale at which you apply your analyses can result in potentially huge errors. One way to approach this problem and to get over this to the extent that you really can is to consider what's referred to as the bulk scale of the aquifer, which is taking values over a large area and then applying some statistic evaluations to try to determine what the average is and to basically weed out or eliminate the effects of some of these huge variations and to give you values with which you can make some level of predictive determinations as to the behavior of the aquifer over a larger scale. And again, note that the same scaling effect would apply to all the hydraulic characteristics and the various parameters, not just the specific capacity. The specific capacity does reflect how much storage is at work and what the hydraulic conductivities are right in the vicinity of where these monitor wells were drilled. So they're all going to be in the same boat with having this kind of scaling effect. And to some degree, water quality could also be impacted by this. Maybe not to the same large extent, but you will see it in water quality as well. So what do we do with this kind of variability and uncertainty? And one answer, aside from the averaging that I just talked about and trying to get bulk scale, is also to focus on what's referred to as the water balance, which we're going to be talking about quite a bit today. It's also referred to as water budget. You'll see that both terms in our slides. We're going to get into that into some detail today. So on to the next one, and this is going to be handing the baton back over to Anne to talk about aquifer characterization.
Well, thanks, Bill. You make the work a little challenging. You've set us painted a picture of an absolute complex challenge, but have no fear. There are ways that we can figure things out and do characterize. And so we're going to drill just a little deeper to see what some of those tools are. First, let's set the goals, though. So what are the most important and achievable aquifer characterization goals? Well, they fall into two buckets. The first one is in critical determinations. That includes the aquifer water balance, safe yield, and the assessment of supply and demand. So this will inform how the aquifer functions. The second category includes items that lend themselves to further aquifer understanding. These are the dynamics of the aquifer in response to human development and impacts from climate changes that alter the hydrologic cycle, for instance. These include aquifer response to wet and dry seasons, sea level changes, and the inland extent of tidal fluctuations in the context of water availability and quality. So in general, consideration has to be given to the level of current and future resource protection measures, as well as identifying priority areas that exhibit the greatest potential for vulnerability and require immediate action. So let's look at those data. We're going to just drill down a little further here. So on the left are reasonable targets for those bulk scale properties that Phil was just talking about. And again, that speaks to how the aquifer functions. These include hydraulic conductivity that describes how easily a geologic medium can transmit groundwater. Specific yield, that's that drainable porosity of the matrix. And recharge, it's expressed as a percentage of rainfall. On the right side of the graphic or the slide is time variant parameters that are integral to a monitoring program. This data is captured from publications, well and water use information, hydrochemical analyses, and hydrogeologic mapping. Some of this data is from records, and other data can be collected from wells to determine annual seasonal variations over time. One of the primary sources of good data is going to be from an aquifer test. And an aquifer test is used to determine that groundwater availability. So it's integral to understanding and managing the resource. It's accomplished by applying a known stress to an aquifer with established hydraulic boundaries and observing the water level response over time. In other words, construct a well, pump it, and monitor the results, and look at that in the context of its regional environment. Formal pump testing is typically part of constructing a municipal drinking well, although even smaller domestic wells and monitoring wells can have abbreviated tests run to determine flow and drawdown, which are still valuable data. Well drilling and aquifer testing can be expensive, so the proper planning and design of a well and pump test will assure useful results. The outcome of testing or estimated values of aquifer hydraulic properties at that well location. So collectively, when we have a lot of wells and a lot of test data, it provides an understanding of the regional groundwater availability and geochemistry. So where to begin? The first step is to collect and compile that information. And it would include groundwater and surface water, water quality, geophysical data, geologic information in the area of interest. So based on that collected data, the second step is to develop a conceptual model, which is essentially a simplified representation of the groundwater system. An example of that is in this middle graphic. This is taken from some work that was done a few years ago in the Savannah province. So you can see that it's talking to and pointing out groundwater flow patterns. So now we've got something to work with. Aquifer testing calibrates that conceptual model for the well location by providing actual field data. So in the bigger picture, supported by this collected data, numerical groundwater flow models, variable density and transport models can be used to simulate groundwater and water quality conditions based on different withdrawal scenarios. This is really important, especially to understanding aquifer response in things like drought conditions or in areas of known contamination. The results are used to establish groundwater management strategies. As summarized in this graphic to the lower right, this compares aquifer characteristics of various types, including the karst aquifer, and as Phil mentioned, highly variable, highly heterogeneous in comparison to the other types. So the message here, and you'll hear it over and over again, is that these order of magnitude ranges need to be considered, as well as the application of bulk scale hydraulic values versus field values that can be acquired over time. This is where weight's given to understanding that water balance, the water going in and out of the aquifer, and it also underscores the importance of long-term groundwater monitoring. Remote sensing is another way to collect data. So under this banner, there's many cost-effective and useful tools like surface geophysics, including resistivity surveys. This is a picture of that was sent to us based on some training that staff experienced a couple of weeks ago. So we were really glad to see that that you've purchased equipment and were training how to use it. Other methods would include things like another geophysical method, which is a ground penetrating radar. And that uses electromagnetic waves to determine the presence or quality of groundwater to some extent. Another useful tool is the tracer test that is conducted by injecting dye into the aquifer to determine groundwater flow direction and velocity. One of the bigger, snappier tools is satellite imagery, and this presents a tremendous opportunity to observe and monitor the Earth's surface for various reasons, from weather forecasting to ocean temperatures. This is a special case of digital photography through radiation bands that are bounced off the Earth's surface or collected passively by satellite sensors, and then they're stored digitally as pixels. So a few of these products I wanted to talk about, a few of these missions, the original GRACE mission and the recent GRACE follow-on mission satellites, they continually monitor changes in ice sheets and glaciers, near surface and underground water storage, and the amount of water in large lakes and rivers and, I don't know, potentially cenotes, as well as changes in sea level and ocean currents. The surface water and ocean topography satellite, it's known as SWOT, S-W-O-T. It's due to be launched soon, and it's pretty exciting. It's game-changing in that it's an instrument called the K-band radar interferometer, and it bounces radar pulses off the water's surface that not only measures the water height, but it can also calculate changes over time. So pretty groundbreaking stuff. The Landsat 8 satellite imagery that can aid in tracking water quality changes within the water, like sediments flushed into the rivers by erosion and then that occur further inland and then express themselves at the mouth of the river. Or it could be that it could track nutrient blooms. So these images are of Belize, of the Belize River, that show a dramatic comparison between 2018 and 2019 sediment discharges. So a very valuable tool that can be used not only to see things holistically, but I'm kind of guessing you could take this and track back to source or sources of sediments. So you can kind of zoom in on areas that may be the point source for these sediments. So with any of these tools, satellite tools, the resolution varies from broad spectrum to a fine resolution, and they're dependent on the satellite orbit and coverage, the type of radiation band, and the processing. There's been great strides in combining frequency bands through the use of artificial intelligence. And last, I just want to keep in mind that the data is open source, and for the most part, my knowledge is free of charge, so it's well worth investigating for application in Belize. So finally, I want to talk about water quality and data standards. This is understanding these hydrogeochemical characteristics is really critical to understanding groundwater management. Groundwater chemistry depends on a number of factors like geology, the degree of weathering of rock types, the quality of recharge water, the degree of other sources like that could be related to land use, like we just talked about, sediments, human activity, and other environmental variables. So groundwater quality assessment is really important to safeguarding the water for human consumption and the environment, and to identify those sources of contamination and areas of vulnerability. So in order to characterize groundwater, samples can be taken from a wide range of constituents, like the ones shown here in these parameter categories, or it could be from a select number of specific parameters that are of particular interest. These are all collected using standardized field collection methods and then analyzed through established laboratory protocols. The results of these data are compared to drinking water health standards to determine the level of acceptability. Belize has adopted drinking water standards from the World Health Organization and the Environmental Protection Agency in the US. The Integrated Water Resource Act of Belize includes many regulatory references to safeguarding water resources and minimizing pollution through governance, although it appears that at this moment that governance may be falling short of strict enforcement. So what is the score, the quality score for the basin? I think it's ranked poor. And it's based on some very fundamental inputs, and that is that appears to be inadequate disposal of household, agricultural, and industrial liquid and solid waste. And another big player is related to land use practices that contribute to significant erosion rates and sediment loads. So with that, I'm going to turn it over to Phil to talk about regional flow and water balance.
Thank you, Ann. And if we can just go ahead into the next slide, which is going to be on topography and drainage. You might ask yourself, oh, gee, topography, that's nice. It's kind of, low and flat up in the Corazal Basin. What's important about that with respect to groundwater? Well, hopefully by the end of the day today, you'll understand that the topography actually is quite important with respect to what can happen with your source of water in the ground, which is the freshwater lenses. This slide here on the right presents the topography of Belize, and it's readily seen that the Corazal Basin overall is generally low in elevation. Any of these areas that are in darker blue along the coast are 11 meters or less in elevation. And then the areas in those two kind of difficult to discern shades of purple that are comprised most of the Corazal Basin itself are indicating as being under 53 meters or so in elevation. So the basin's relatively flat, and this is an important point, relatively flat with moderate slopes coming from the more central area eastward and northward, northeasterly down towards the coast. So why is that really all that important? Well, here's why. The three main rivers that are in the Corazal Basin, being the Rio Honda, the New River, and the Belize River, transit the basin. You can see them, Ann's pointing them out here. The first two, the Rio Honda and the New River, are pretty easy to follow because the incised channels are fairly easy to make out in the change of color in the darker blue and the blue, and as against that more of a pinkish color. The Belize Basin is a little more amorphous, especially right around the city, but you do get the general sense of it. These rivers will seasonally contribute varying amounts of water to the aquifer via leakage along the river channels and infiltration in the river channels themselves, but especially during flood events. And this is why this is so important. because the entire basin can be vulnerable to flooding when it's as flat as it is and with the general slopes. It has two impacts. If the rivers overflow their banks, then you've got an awful lot of water that's going to be flowing out to ground that's relatively porous, and it's also not sloping very steeply as a generalization. That means that a couple of things are going to be happening. One is that an awful lot of water that could be potentially quite contaminated during a flood event is going to be onto the ground. It'll be available to flow perhaps directly into the formation or into the aquifer via the open cenotes and things, but also just through the percolation through the epicarstic zone and down into the aquifer when the water is not running off as fast as might be desirable otherwise. So it can be a real problem. And these rivers can contribute very large volumes of water out to the coast, especially during the rainy season, can produce that kind of sediment loading and that sediment plume that can have an impact offshore as well as just right with the aquifer itself. So this all can be a real potential threat to the water quality of the aquifer, and also can impact the overall water balance, which we're going to be getting into now in this next slide. But before that, just think for a second. If we've got an awful lot of flood water that's gotten out onto the ground, is percolating down in, what's going to happen? The amount of water that's in storage is going to go up, and the water table itself is going to come up. That has implications for a lot of different things. So we can go to the next slide, Anne. So aquifer flow patterns and water balance. As we noted earlier, because of the gross uncertainties that are inherent in karstic aquifers, one way to proceed in characterizing these types of aquifers is to focus on the water balance or water budget and incorporate those bulk aquifer properties as appropriate. As we've discussed, the water balance is the sum of all the water in and all the water out of the portion of the aquifer under consideration. And ideally, you would want to go with perhaps the largest portion of the aquifer that you can reasonably assess, because then you'll have perhaps the best average parameters. Now, as per this graphic, which is kind of a cross-sectional cartoon, if you will, through the Yucatan aquifer, note that there's no scale on it, nor is there any indication of the solution features, but they are obviously there. Per this graphic, there are a few items where you can get a reasonable quantitative summation, including precipitation. You'll know pretty much, I think, what's falling onto the ground. There's weather stations, and that information should be readily available. And precipitation recharge. There's good estimates that are in the literature of how much water is likely to get through the surface and down into the epikarst and down into the aquifer. Those values can be applied to any predictive type of assessments. Estimated evapotranspiration, that can be fairly accurately developed through both activities right on the ground with pan evaporation measurements and those types of things. Or, as Anne pointed out, you can get larger scale estimates of evapotranspiration by using remote sensing and the satellite data that she was talking about a couple slides back. A very important part of this for getting accurate assessments of just how much is getting into the aquifer versus running off or being lost to evapotranspiration. The things, for instance, of pumping, which is one of the big components here, and can have a major impact on the aquifer if it's allowed to develop to a large scale, is exhibited there in the center of the diagram, where you've got well pumping coming out. And this can be for any number of reasons. And obviously, with the distribution of population and where there's developed areas and agriculture areas in particular, the pumping can be very concentrated in some areas and very sparse in others. So that's something else that's going to be important for you to know about and to be factoring into any design of a monitoring system as you go forward. Such things as the river leakage, how much is coming out of the river channels themselves, groundwater seepage, inflow via cenotes, underground outflows to the ocean. These are likely to be considerably more difficult to assess, but you may be able to work out some idea of those by dealing with the parameters that you do have a good handle on within the water balance itself. Also, there's likely to be some literature-derived estimates that are out there that could be found and incorporated into your assessments of the water balance. Now, one thing to keep in mind here, the water table is exhibited on this, this cross-section. It's diagrammatic only, but it's important to recognize that as temperatures increase and during drought periods, another aspect of climate change, evapotranspiration is likely going to increase in a potentially nonlinear fashion. So this could seriously impact the amount of precipitation recharge that's going to get back to the aquifer, and which is going to also impact runoff to the ocean and, again, the overall water balance. So the water table can fluctuate with the changes in evapotranspiration as things get hotter and drier. Conversely, if you have more intense rainy periods, which is a phenomenon that we've seen in other areas as a result of climate change, longer droughts, but heavier rainy periods, this could change again. So the water table can be fluctuating. Obviously, knowing what's happening with the water table is going to be extremely important, because where the water table is going to control the volume of water that's in that freshwater lens, because it controls the thickness of that freshwater lens. And we're going to be seeing something about that a little bit later in this presentation. So it also shows, in kind of a cartoonish fashion, the regional cross-sectional flow paths that could exist in an equilibrium scenario, or even in a dynamic scenario where there are more stresses being put on. These could be changeable, but in general, it's going here from left to right. The freshwater lens has freshwater underflow coming in, saltwater underflow coming in below that mixing zone, and all headed out towards the ocean. You've got runoff going down, and so this is going to be the general flow path. But keep in mind that increased pumping can change, the gradients can change these flow paths. And this doesn't factor in the effects of some of those faults that can be out there that we know they're there, but we're not exactly sure how they impact lateral flow to the aquifer itself. So more unknowns to contend with, and to make your life just a little more interesting in designing a monitoring system that can go as far as possible in being able to identify and characterize some of this. So now if we can go to the next one. The Corazon Basin water budget. So this slide presents, but really the primary components of the water budget are the water balance for the basin itself. And one useful way to conceptualize the water budget is really to think of an analog that you probably are all very familiar with, and that would be your bank account or your checking account. I mean, if you have more money that you're taking out of your account than you're putting in, you're going to see an immediate change in the amount you have in storage. What's the balance in your account? The same thing is exactly there with a water budget. And since the concept of safe yield that we're going to be discussing here in just a couple more slides, Anne has already touched on it, it's derived from having a solid understanding of the water budget. The more confidence you can have in the values you're developing for all of the components, and therefore you can have a better ability to make estimates of what can change and what is the safe yield of the aquifer itself. So we go through these, look at the water in, some of the obvious things, infiltration of the rainfall through the epicarstic zone down into the aquifer. You've got cenotes and open water lagoons. You've got river leakage, and that can be both the more common flow situations where it's not a flood stage, but you've got water coming down and it's in contact with the epicarstic zone, and water is leaking through the riverbed itself down into the aquifer. Obviously, during flood stages, that's going to be covering a huge area, and there'll be more of that going on. And then groundwater seepage. Another way to put this would be groundwater inflow or outflow. And this could be groundwater moving through the Yucatan Peninsula itself, including this idea that there might be some groundwater inflow coming across the border from the north and northwest from Mexico. So that's a component of it. It's very difficult to characterize that at this point, but that's something you maybe get a better handle on over time based on literature research, and also some monitoring information may give you a little bit bigger picture of that. The water that's going out, obviously a big chunk would be evapotranspiration, direct evaporation off the land, and then transpiration by the plants. And this would include grasslands, heavily vegetated areas with heavier brush, larger tree areas, and then agricultural areas where they're actively growing and irrigating crops. So that's a big water out there. And then water supply abstraction, the pumping from the aquifer for drinking water purposes for municipalities and smaller developments and villages in the areas. A probable big use would be for agricultural and for irrigation, especially during the drier periods. And then all the other industries and commercial activities that can be out there that require water to process whatever products they're manufacturing. And then finally, the rivers, springs, and conduits that can take water and lead it out to the ocean. And this can be the underground outflow via the solution conduits. It could be some springs. There may be some of those down along closer to the coastline, and also the rivers themselves will be taking water and transmitting it down through to the ocean. If we can go on to the next one, let's just move on from this to the water balance and the change in storage. And this is getting into some really important concepts here. So right now, from what we know, it's likely that in the Corazon district, it's likely that the precipitation recharge, which is the overall source of water, significantly exceeds the current levels of abstraction. So what will be most important, the most important aspect over time, is that ratio of total recharge to the total pumping withdrawals. And by the total recharge, I mean what really does get down into the aquifer itself and can add to the amounts that's in storage. So having said this, though, you have to be very aware that it's not really all that simple. Again, we have the nature of karstic aquifers being so extremely difficult to characterize. And so this can cause unexpected impacts on the overall aquifer conditions, as we discuss more in the next slide. On the graphic on the right is an interesting one. This comes from an example of the Central Valley of California. This is based on some real data over time. You can see the time period on the bottom going from about 1962 all the way up through about 2014. So it's a long period of time. And what we have here is changes in the amount of water that's in storage, which is depicted by the red line. That's a very large red line descending from upper left to lower right. And what that's showing is that the amount of water that's in storage is dropping, in this case, pretty rapidly and over pretty significant levels. And this is even in spite of the increased water deliveries that they're making during wet periods, during what's referred to managed aquifer recharge, which is the shaded green areas here. And you can see there's significant amounts of water that's being put back in. But nonetheless, the water in storage is dropping. So this is a lose-lose situation here, because eventually you're going to run out of water at some point. And so even in spite of as much water they're putting in, they're losing storage. So what is happening here? Well, the obvious answer is that they are over-pumping this aquifer. This is exactly what you do not want to have happen in the Yucatan aquifer. So this is why the water balance is going to be so important, and why the safe yield is going to be so important. So keeping in mind here some of the points that are here on this slide with the groundwater and surface water interconnectivity. It's a linked up system. The surface water changes as a result of changes in the groundwater. And well pumping, if it's greater than precipitation recharge over time, you're in a net loss situation. So if we look at what's on the lower right, is something called the continuity equation. And this is the basis for safe yield. And really what it is simple. It looks very simple, but this equation is used in a number of different types of things that can get very, very, very complex, because the ins and the outs components can become very complex and very numerous. But basically what it says, in minus out is equal to the change in storage. You think back on your own checking account budget, there it is. If you take out more than you're putting back in, your account balance is going down, and that's not a sustainable way to proceed. So given that one of the prime components of your monitoring project going forward, and for management of the aquifer going forward, is to not result in something like what you see on this graphic from California, then this is very, very important. So the graphic on the lower left is basically kind of giving you some idea of what happens during let's not say summer and winter, because that probably doesn't coincide exactly with your dry and wet periods, but substitute those terms for the winter and summer. So you've got an unsaturated zone and intersected by a river. It's a little out of scale there, but you can have a water table that's reflecting those changes going up and down. And so the more pumping that takes place, the greater the fluctuation that's there. And this can have some unforeseen and unpleasant results if this dry versus wet season storage chain gets to be too big, because you're now pumping the aquifer more. It can result in a number of potential impacts. There's upwelling of saline water where the lens is a little more shallow, increased saltwater intrusion along the coast if the impacts are being felt there, impacts to water quality as you might expect. And then one that doesn't get talked about very much, but is a real factor with karstic limestone environments, and that's land subsidence. If you remove a lot of water, the water table drops significantly, and now you have solution features that were once full of water that are now dry and open to atmospheric conditions. The limestone can begin to deteriorate rapidly, and you can have collapse of the roofs of those solution features and can create a sinkhole that can be very, very dangerous for anything that's on the surface there. So it's important stuff. So with the continuity equation in mind, let's take a look at safe yield, which is the next slide. So what exactly is it? We've got one pair of definitions here on the left. First one, sustainable pumping, essentially sustainable abstraction. Well, it doesn't say a lot. A little better one is balancing the needed withdrawals against the negative potential impacts to the resource and the environment. That's a pretty good one. But a better one is slightly more detailed than this, and it comes from the Belize National Integrated Water Resources Act, which says that safe yield means, and I'm quoting here, the amount of water which may be abstracted from an aquifer at a rate which would not reduce the supply to an extent as would render such abstraction harmful to the aquifer itself or to the quality of the water, and would not affect the economic feasibility of other abstractions. Now that's quite a mouthful, but it's extremely important in terms of sustainable integrated water resources management. Once again, you must always recognize that safe yield is a dynamic concept. Any changes you make in that water balance could potentially and will likely impact what the safe yield will be. Now, over time, these changes may be fairly slow and not reflect immediately in the water balance and in the safe yield calculations, but it's something that has to be kept in mind. You must always recognize that safe yield is a dynamic concept. So the graphic, which is here, is an interesting one because it's a positive thing to consider right now. This is looking at a period from 2004 through 2008 for both potential evapotranspiration, actually 2000 to 2008, and then actual evapotranspiration 2004 to 2008 for the Yucatan Peninsula as a whole. And you can see the northern part of Belize, essentially the Corozal Basin, is included in these 4 different panels that are here. The top 2 left panels, the 2 left panels, top and bottom, present, they show that the actual groundwater recharge, which is on the bottom right, is fairly high. And so the precipitation, which is on the upper left, exceeds the overall actual ET, which is the lower left, which is the actual evapotranspiration. And the upper right shows the potential evapotranspiration, which you can see that there's quite a difference between the potential and what the actual is. This means that there simply could be much more use if there was more heavy irrigation and things going on. This could be a threat if more agricultural development gets going. The potential for much higher evapotranspiration is there, and that could cut back. But right now, it appears that the amount of water being pumped out is greatly exceeded by the amount of recharge that's getting back in. And so this is a positive note. It's a good place to begin. And so you're at a good point in terms of beginning to establish baseline information on the aquifer and how it's being operated or utilized, I should say. Now, again, each of the groundwater budget components must be quantified to the extent possible, and noting that it's difficult, as we've said so many times. One way to get around this also is if you're going to look to make any kind of predictive estimates of things, factor in significant safety levels, safety factors, and also the dynamic nature of the system. There's no one snapshot in time that's going to be able to hold up over longer periods of time, because if things change, both seasonally with wet and dry periods, just for as an example, but also with what's coming with climate change and those types of things. So with that, now we're going to go back to groundwater vulnerability, and I'll hand it back to Ann again.
Thanks, Phil. Such fascinating stuff. I mean, it really is. It's just, I just never tire of it. No matter where you place this, these models and these concepts, when you hone it into your area of interest, things just become more apparent, and there are pathways ahead to figure it out. And so it is a very exciting time, as you said. As a side note, the Integrated Water Resource Management Act of Belize is a really fine document. It is a great guiding document. It's very complete, and making the contents of the act actionable, and really pulling together a management plan is, it's got great bones. All right, enough of that. Let's talk about groundwater vulnerability. So water quality degradation is one of the most pressing water resource issues. We've talked about that. It really is. And there's certainly acceptable water quality that can be located. It just, one has to be aware that poor quality groundwater occurrence, it's growing, and it has a number of sources. So I just want to talk a little bit about those sources. Many of them have already been covered, but let's cover it again from a different angle. So saline intrusion. So there's high concentrations of chlorides that are found along the coast and along rivers that are subject to tidal effects, storm surge and sea level rise, and overpumping, all encourage saltwater intrusion. This is a big factor for an area that has, the presence of large rivers, and it's coastal. Seasonal recharge. So we talked about that. Recharge can, or the droughts, the dry season can extend 3 or 4 months of the year. So you can really expect poor water quality during those periods of the dry season when there's just a reduced amount of precipitation. Land development and deforestation increases sediment loads and the turbidity concentrations. It can overwhelm the filtering functions of those coastal mangrove ecosystems that protect and perfect probably that environment, and the important barrier reef systems. Improper agricultural activities that can also result in that loss of surface soils and contribute to nutrient and chemical pollution of water resources, and in particular to the areas around the ag areas of that depend on groundwater, the rural wells and water systems. Lastly, untreated wastewater and industrial runoff also contribute significantly to water quality degradation. There's not a lot of available information on water resource demands. So I tried to scale this up so that you could see what are the biggest demands. We know that there's more surface water that's used presently than groundwater for both industry, with agricultural ranking #1, and for domestic use. On a basin level, the use of groundwater mostly is used by agriculture. Some augments urban water supplies, except in places like Corozal City and Orange Walk, where that's the primary source of drinking water. And rural areas are almost exclusively dependent on groundwater. Basin agriculture is focused on the areas around the Rio Hondo and the New River watersheds, which makes a lot of sense. This is a ready area that gets and receives water, both again from surface water and from groundwater. And this area is growing. I went through this exercise of using Google Earth to be able to trace what appears to be cropland, and it's a pretty significant compared to some historic graphics that we had researched. It looks like this agriculture area is really growing. In red are the settlement areas, just for reference. Again, Corzal and Orange Walk, not sure about Shipyard, but those two settlement areas do depend on groundwater. So it's in direct competition, both in water quantity and quality, with agricultural areas that surround those towns. On the left-hand side is an infographic, and it really represents all of Belize, but I think it breaks down the statistics that could be referenced for the Corzal Basin area. So it shows that agriculture is a significant water use. Okay, so that's 68%. That's significant. It also suggests that there's limited data on the types of irrigation practices, and also that there's a high to moderate use of fertilizers and pesticides. Let's talk a little bit about the demand forecast. So we've been saying over and over again, there's freshwater supplies that are available to the current population. Again, this is such a great place to be starting a management program, is because we know that there's increasing stresses on these supplies, and they're due to two main factors: population growth and industry, and also the effects of climate change, including extreme droughts. So on the left are projected changes in rainfall and temperature. The current average rainfall in the north is about 60 inches. By 2050, that average is estimated to drop about 8 inches. While the change in annual average temperatures from a current 84 degrees Fahrenheit are projected to increase to 87 or 88 degrees. So it's pretty significant. It's fair to say that the dry season ET rates, as Phil had mentioned earlier, will increase, and the wet bulb temperature in the wet season will feel very steamy with high temperatures and just typical high humidity, somewhere in the 80s, 80 degrees or 80% humidity. The demand forecast, which is that graphic in the background, this was very generalized and it's not specific to Belize, but I think it paints a reasonably good picture of what's possible. It describes water demand under two climate scenarios. Those are the purple and red lines. And it shows that there is a significant amount of demand increase over time. It also illustrates that implementation of adaptation strategies, in this case, improving irrigation techniques, that's the lines in light green and blue, can really be effective in decreasing demand. You can see that departure right around, you see it really departing from 2021, and it starts to increase its departure through that 2093 timeline. So this really emphasizes that there are mitigation and management strategies that can be employed across all sectors to address climate change and increasing demands. So it is a hopeful picture. Again, it's a management strategy, and I know that Belize has pretty extensive coverage on mitigation strategies. Joined with groundwater management, it'll be a really good complement to understanding the system. So we don't have a transition slide here, but I'm going to slide it over to Phil to talk about sea level rise projections.
Thanks, Ann. Yeah, we're keeping within the overall concept here of vulnerability. Thanks, Ann. And sea level rise projections. Well, this ties right in with what Ann was just showing for what's coming with respect to temperature changes, which are going to have a big impact. Obviously, the sea level is going to change as well. We know it's happening. So the study area is north of the Belize River. So what we're looking at here is right down around Belize City itself, and a little bit out of our area of focus here. But nonetheless, this will get the point across. And what we have here is the potential impact to low-lying coasts and watersheds of the rivers from projected sea level rise based on a global warming of 4 degrees, which is depicted on the left, and 2 degrees on the right, and these are both Celsius. And it has to be repeated again and again that while those numbers don't sound big, 2 degrees or 4 degrees, global warming of 2 degrees is going to be awful. Global warming of 4 degrees Celsius is going to be catastrophic. So these are things that we don't want to see happen, but this is a good example of some of the ramifications along the coastline. So you can see here that the saltwater intrusion, well, first off, you can see just how far in you've got flooding going on, especially in the Belize City area. It's much more dramatic on the left than it is on the right, but there's areas along the coast now that are going to be inundated from this. And that's a very serious issue to have if you're thinking about, my gosh, how are we going to protect a city from something like this? But even more so with respect to the water supply, to the extent that water is being produced in these areas, for instance, around Belize City, from groundwater in the future, and even more, this is going to drive saltwater intrusion further into the west, which means you're going to have either eliminated a portion of or significantly reducing a good chunk of the freshwater lens that's going to be, your only supply of fresh water there. So this is a real serious concern, and it is a major threat. And this is why I think monitoring with what we refer to from our Bahamas project as sentinel wells, it's basically a monitor well that gets down to where the saline interface is, where you've got the freshwater lens transitioning into the saltwater underneath. Knowing where that is as a baseline, and then being able to monitor changes in that over time as sea level comes up and as pumping may increase due to increases in population and all the things Anne's just showed on that previous slide. That interface, if it begins to come up, these sentinel wells, the data you can get from them on what's happening at depth, they can be your early warning signs and your early warning system as to something bad is happening here. And we've got to do something to protect the water supply, either pumping from shallower or going further inland with your water pumping, or finding ways to recharge more fresh water back to offset some of that saltwater intrusion. So this is a pretty significant threat, maybe not tomorrow or next week, but going forward in time, this is a real phenomenon that needs to be taken into account. Could we go to the next one, please? So this is why this is so important. The freshwater lens we've talked about a lot. The graphic on the left gives you a good idea of what this really does look like in reality in a cross section. The slide itself presents an extremely important concept that applies to the Yucatan aquifer or to any aquifer where karstic limestone comprises the peninsula geology, and where you've got ocean on at least one side, if not both sides, like in an island, for example. This relationship that's known as the Geibin-Hertzberg relationship, and is presented on the leftmost graphic here, it states that the thickness of a freshwater lens at a given point on land will be governed by the elevation above mean sea level of the water table at that point. So as you see here, as you go kind of to the west or to the left in this graphic from sea level, the higher the water table is, the freshwater lens is getting proportionately thicker. Well, that proportion is 40 times. That's the Z that's there. And as you see above, the height of the water table at a given point on land over sea level, mean sea level, is going to be 40 times the depth of the freshwater lens at that point is going to be 40 times that height in H. So a pretty simple and basic equation, but it's a very, very important one, which means that if you lose your water table, you're going to lose your freshwater lens thickness proportionately by a time 1 to 40 times. You drop the height of the water table by 1 foot, that freshwater lens is going to reduce by 40 feet. Very important to keep this in mind. So this relationship, by the way, has been verified in many studies and can be considered a valid and reliable predictor of freshwater lens thicknesses. Note that since it is based on density and the specific density of saltwater versus freshwater can vary over a small amount, that 40 might be a little fuzzy, but for all intents and purposes, it's a good constant to use and it's a good one to rely upon. So this is especially important, as we were just talking about, with the coastal areas of the horizontal basin, where the ground elevation is relatively low and the lens is thus expected to be quite thin to begin with. It's in these areas where there'll be the lowest thickness of fresh water to start with, and where any significant pumping can have the greatest impacts, as is depicted on the graphic here on the right. And what we have here is a pumping well in this diagram that's near the coast that has been pumping, and it's impacting the local gradient around that well, which is causing the saltwater interface to rise up to where, in this case, you'd be pumping potentially saltwater or extremely saline water out, and you've really impacted your freshwater lens. Well, this is only depicting a single well in this example. Obviously, if you have significant amounts of increasing pumping along the coastal areas, you're going to get this kind of thing happening on a much larger scale. And I think, as Ann could attest to, it is a big problem on the coast of Florida, down in the southern Florida area, where they're having to deal with this on a very large scale. It is a real thing that's happening. So in the areas of the basin that are more inland, however, as we pointed out before about the topography, and this is why that topographic map was important to start with, it can reach to over 50 meters. And from the Geibin-Hertzberg relationship, you could thus assume that the thickness of the freshwater lens, as you go more inland from the coast in the Corozal Basin, is going to be substantial. But you've really got to be careful with this broad assumption, because it really depends not on the ground elevation, but what is the elevation of the water table. I mean, that's what's depicted in the graphic on the left. It's not the ground elevation, it's the water table. So obviously, if the water table is some distance down from ground level, then you've got that much of a thinner freshwater lens underneath you. A thinner lens means less in storage, and it means that it impacts your water balance, your safe yield. All of that's controlled by that water table to freshwater lens thickness relationship. So assuming that the lens in the inland portion of the basin is still substantial, and given conditions right now, that I think appears to be what's there, that there's still a tremendous amount of water that's in storage in the ground. The biggest near-term threat, and this is not to downplay the impacts of Geibin-Hertzberg, but still the biggest near-term threat to the resource itself would be, I think, not saline water upwelling due to pumping right yet, but the water quality impacts that we've mentioned before from surface-derived contamination from any number of different sources. So if we go on to the next slide, Ian. So we mentioned earlier the potential vulnerability and the potential damage from flooding. Slide on the left is a map of the northern portion of Belize, from really it's basically the Corozal Basin, and it depicts flood hazard areas. I mean, sorry, the one on the right is the flood hazard area, but the one on the left just presents a little easier to see the three rivers that we've talked about and the general aspects of the landform there itself. Now, on the right, however, is a map that presents the flood vulnerability mapping for this portion, which is essentially almost all of the Corozal Basin. It's obvious right away that the river channels themselves are extremely vulnerable to flooding. You can see both the Rio Hondo and the New Rivers there, and then some reflection of the Belize River down kind of on the lower right, lower central right. But it's not just the rivers themselves. As we said before, if there's widespread flooding and the rivers are coming out of their banks and flooding out into land, look at all of the snow taters that are up there and open lagoons. There's hundreds of them up in this area. And so this is a point where any flooding, even if it were to stay just relatively close to the river channels themselves, it can still move an awful lot of water that could be highly contaminated with sediment, pollutants of any kind, industrial waste, et cetera, directly down into the aquifer. So while there's not an awful lot, I think, that can be done to stop this at any one particular point in time. I don't know if Belize has any contemplation of flood control dams, but in the future, this would be something that really might be worthwhile for consideration, because otherwise you've got an aquifer that's extremely exposed and vulnerable because of the flooding potential. So I would also suggest that as part of the monitoring plan going forward, it should be considered having fairly intensive water quality sampling and monitoring in these areas, and especially since you do have the cenotes that are open bodies of water. You've got a free non-drilled way of getting samples of water that are going to give you a real good idea of how things are going in the aquifer, as well as water table. So this is something to consider, and it would help establish baseline water quality information right now, and to spot trends both in a local sense and a larger scale sense of degradation over time. We can go to the next slide. So this is a transition slide, but I'm going to keep talking here till the end. What would be the next steps for the hydrology unit? Well, we'll be getting into some of this in a much more detail in the final webinar coming up later in August. But we can provide some framework in this presentation that will provide the introduction to what can assist the hydrology unit moving forward. So what actionable steps could be involved in your planning and choosing actionable steps? So for that, if we can move on to the next slide. And now this one presents quite a bit of information, and so I'll go through this fairly quickly. But as you can see, it's broken down into three main categories that are under the overall heading of groundwater data and management. So the first column presents basically our understanding of the current status of the groundwater monitoring program. It points out that there is, right now, to our knowledge, no real central database of information relating to the groundwater resource itself. And then it also states that there's uncertain quality and usability of the limited data that you may already have. It also reiterates an important fact revealed in our research for this project, which is that there's very limited published data that we have been able to find on the Belize portion of the Yucatan Aquifer. The last point in this column is that it appears there is essentially no serious enforcement as yet of regulations and administrative procedures that relate to the use of groundwater at present. So now the second column, which is what we've designated as phase one planning, essentially the steps to begin the overall program. So we'd have forming a team, determine and define those goals and objectives, assess what existing data you have, determine the data gap, which is what data do you need to actively really assess and characterize to the best possible extent that you can what's going on in the aquifer. Very important, the next one, select your database platform. How do you want it to be set up? Who can access it? Where is it residing? What's it going to include? What kind of interactive data does it have? Is it automatically updating from transducers and telemetry from field data, or is it all based on field sampling, those types of things? Can it integrate graphical output? Can it integrate satellite information? All of that has to be worked into the design of this and choosing what kind of a platform you want to use. And then obviously all of this is going to require some funding, so that has to be part of the strategy as well. Probably a phased approach where you get some for initial installation of monitoring wells and figuring out where things are going to go, and then develop and approve the plan. The second phase on the last column on the right is to go ahead and establish this implementation of everything you've worked out. Get the budget and scope of work defined, conduct public education and outreach about what you're doing and why. That's an extremely important part of this. Develop the database and the visualization tools so that you can communicate to the public the serious nature of protecting this resource and how valuable that resource is. Get your data collection underway and do your field investigations. And this would include the monitor well installations, having defined where they're supposed to be, and then begin to enforce administratively and via regulations, wellhead protection, abstraction and pollution regulations, and beginning to control and regulate water quality impacts on the aquifer itself, so that you can get a better handle on what the vulnerabilities are and begin to work forward with continuing the integrated water resources management. So with that, if we can go to the next one, Ann. This is conclusions. And as I mentioned, I'm going to give you some final thoughts on what we've covered today and just a little bit of the perspective. We're not trying to force our view of what a monitoring plan should look like going ahead. As much as what we're trying to do is give recommendations on how things based on our experience that have worked can work for your benefit as well. And we will be getting into much more of this in the next one. But you're now embarking on your effort to monitor and protect the Yucatan Aquifer so that it can be sustainably managed off into the future. In the next webinar, we will present these potential ways. It's not dictating, but presenting potential ways in which you can implement such a program. And at this point, the data we've reviewed indicates that from a supply standpoint, the aquifer is in pretty good shape. Some would even say potentially excellent shape, with a recharge and storage supply that exceeds the current estimated levels of abstraction. Water quality in some areas locally may be a different story, but let's just leave it with that on a positive note. This fact, however, should not lead to any complacency or to thinking that there's no urgency. There's numerous examples from the United States that can confirm that over abstraction of aquifers, even aquifers of enormous scale, similar to the scale of the Yucatan Aquifer, they can be seriously depleted in surprisingly short periods of time if unregulated pumping is allowed to run out of control. Now, there's a saying along these lines that I have heard for many years, going way back in my career, that I find to be particularly appropriate. And I've worked in a couple of situations where this kind of foresight came true. And it's this, and I'm quoting, "Once the straw is in the cup, it's really difficult to remove it." Think about that. What this means is that once water users, for any reason, whether it's domestic, drinking water, municipal, commercial, agricultural, so on and so forth, once they've constructed wells and have become used to being able to take this water, even if it's under a regulated permitting kind of process, used to taking this water from the aquifer, it can be extremely hard to get them to stop. How do you tell someone, for instance, a municipality that's now relying on groundwater as a primary source, that, oh, you're going to have to cut back. You're not going to be able to continue to pump as much because we're over depleting the aquifer. So you're not there yet, but this saying should be your guide as we go forward into the third webinar and as you begin to go out there and establish your monitoring plan and work on the aspects of it that we've talked about. Should be your guide in establishing administrative and regulatory frameworks for the sustainable integrated management of the Yucatan Aquifer. So given what we've discussed today, it should be pretty clear that running out of groundwater is not the most important near-term issue as the aquifer resource becomes more and more utilized. Rather, the biggest concern will be with respect to maintaining the water quality such that no net degradation of the resource will occur. So it's almost as if we have a safe deal with water quality as well. How much impact on water quality can you stand as you go forward and begin to utilize this aquifer in a much more grand scale? This means that protection is going to be paramount and establishment of the baseline quality is imperative as well. So as a final words for today, you can't protect something if you don't know what it is. So the monitoring program that you're about to embark on is absolutely the right thing to be doing at this time. And we'll help you to the extent that we can in the third webinar and beyond that, if that's possible even as well. So thank you so much for listening. And we would like to open up for questions. There still is some time left. If you have questions about what we presented today, any of the subjects that came up, you can raise it either in the chat or just raise your hand and Elizabeth can let you in. Otherwise, we do have some ideas of our own and some things that you might want to think about that might be a point for discussion for the remaining time. But I will turn it back over to Elizabeth and Ann at this point and see if there are questions from the audience here today.
Thanks so much, Phil and Ann, for a really excellent presentation, and to my ears, one that was not disrupted by lawn care. So we love to see that. As Phil mentioned, we do have a little over 20 minutes left in the hour, and we wanted to dedicate this time to questions. So if you have them, feel free to either type them in the chat or raise your hand, or you can send them to me in a direct message if you would prefer to ask questions anonymously. That's an option too. So whatever is most comfortable for you. And if no one has any burning questions, perhaps we can sort of get the ball rolling with Phil's suggested topics. and give folks a minute to potentially add any questions. I know there are some folks on phones, and typing out questions on phones can take a little bit more time. Okay, well, while we wait for some questions to potentially enter the chat, Bill, why don't you go ahead and, or Anne, whoever wants to take the first question.
Anne, why don't you go ahead?
Yeah, I'll take it. You're sounding a little hoarse there, Bill. So yeah. So we're curious about how what's happening on the ground. You are the field people. And so one of the things that came to our attention, and I appreciate Tennille and Elizabeth sending us some information on a recent training that staff did on the resistivity survey equipment. I'm really curious, how did that training go? How do you feel like you're going to, where are you going to use it, for what reasons, and what kind of results were you getting when you were training up? Does anybody have anything they can share?
Hi guys. Actually, the resistivity training was in collaboration with Rural Transformation, for which Ms. Cardenas is on the webinar. Without saying too much, the goal for that was to identify groundwater resources for the rural water system. And so we were part of a 1-week course with Rural Transformation staff, showing us how to use the equipment and how to interpret it. On my end, I will say that we definitely need more in-depth training in terms of interpretation of the results. We were introduced to the dipole, the Schlumberger, the Wenner surveys, but I personally don't think 1 week, a couple of sessions is enough, because it's geophysics. It's entirely mathematics. But I don't know if Ms. Elsa has anything else that she would like to add, but we're primarily looking at it for groundwater resources.
Hi, good morning, everybody. Thanks very much, Tennille, for that introduction. Ms. Tennille kind of basically stated the objective of the training, and as she mentioned, the 1 week is nowhere near the amount of time and information that these officers need to actually build on this 1 week session. So, but it is something new for us, and something that was very exciting to be a part of, because it allowed my officers as well as myself and our ministry to build the capacity, and for us to be able to have an instrument that allows us to have valid information on the ground within these areas, so that we could be able to make better informed decisions on where we need to drill, because prior to getting this equipment, we were just using trial and error to drill. So after this training, the officers, with the assistance of representatives from hydrology, they actually went to Halakte to actually do the resistivity surveys and actually analyze the data, because through social investment fund, we're getting funding through them to actually construct a water system in Halakte. And Halakte within the Toledo district was very challenging. They're very challenging in terms of finding a groundwater source, so that these residents can have access to water. They surveyed a specific area, and it was unsuccessful. But they surveyed another area, and they did find some water there. We don't know until we drill the amount of water that is going to be there, but with the use of this equipment, we can determine that when we drill in that area, we're going to find water. So it kind of allowed us, it is allowing us to be able to be very efficient in terms of our finances. So if we had 2 areas that we would have normally drilled, we would want to drill in one, because we know definitely there is no water within that first area that we conducted the surveys in. But as Tennille mentioned, we do need more information in terms of the topography, the soil formation, the geologic aspect of these areas, because with this and gaining more experience in terms of conducting these surveys, and these officers will better be able to equip themselves with making the necessary decisions and analyzing the data that they've gathered through these resistivity surveys. So kind of put in a nutshell what the objective and how that's going to assist the ministry in terms of utilizing this resistivity instrument. I don't know if you guys have any other questions that I could answer in terms of those surveys and the equipment itself.
Do you have priority areas where you'll use the equipment? Is there particular areas that are frustrating you? It's a pretty diverse geology of Belize. Is there certain basins that you've prioritized as being the first place where you'd like to use it, or is it a job by job or project by project application?
We do want to ensure that we do surveys across the country, but for the time being and for the demand in terms of ensuring that residents have access to potable water within the south, there are several communities that have no type of water system. They just get water by hand pumps or when it rains. So we need to ensure that we construct rudimentary water systems within these communities so that residents, as I mentioned, have access to safe potable water. So we are using the equipment to kind of gather the necessary information that we need from these challenging communities. When we did the training, we chose 3 communities that pose a challenge in terms of access to water. Those were Armenia in the Cayo district, Santa Rosa, San Roman in the Sand Creek district, and Unitedville in the Cayo district as well. And then, as I mentioned, after the training, the guys actually went to Halakte in the Toledo district, which poses a huge challenge in terms of finding water. We have drilled about 17 wells in the past, and to date, we have not had the requisite gallons per minute of water that we need.
That's a big investment.
Yes.
So Neil, I see that your hand's raised. I think you have something to add on.
Yes, just to add on, Toledo is the highest portion of the country. And so the elevation is really high. I think in Halakte, it was about 30 meters above sea level where we were. And that's the area that you're looking for, that we initially tried to find water resources in conjunction with ELSA. But additionally, the equipment where you asked what's the usage, different agencies might have different uses for the equipment, and their objectives may be aligned, but the density will make the difference. So for us at hydrology, having that type of equipment, it would allow us to do the type of surveys that would give us our stratigraphy. And so that's the interest for us, as we have to do this for the entire country. So we can't be manipulating Ms. Elsa's equipment because we will have a full-fledged program, a monitoring program to do that. So we're in the preliminary stages through a project, the Green Climate Fund that we're implementing right now, where we have a hydrogeologist who has experience in geophysics and doing resistivity investigations for Barbados. And the geology is similar as with the Grand Bahamas. So having that piece of equipment and having that person on board, we believe that we can get the in-depth training, both theoretical and physical, for us to be a little bit more than comfortable with interpreting the results of those different surveys. So that's all I had to add. Thanks.
It's tricky stuff. Surface geophysics in areas where even you've collected as much information as you can is a tool in the toolbox that sure does help. It's absolutely useful, and we've seen it. It's not the only. It's good to complement the other tools. and when you have nothing else, it is absolutely a fundamental benefit.
And I will point out too, and Tennille, that it's also potentially useful in defining sea level, or the saline interface, because as you know, salt water is going to be very different in its resistivity than fresh water. So I know they can use that that technique for mapping depths to the saline interface, which can be quite useful and less expensive than monitor wells in some instances.
Yes, I completely agree. I've been doing a lot of research into the equipment and the different uses, and it completely aligns with what we're trying to do with establishing a national saline intrusion monitoring program, because we need to establish what that interface is, its depth, its width, and what is the vulnerability to our water resources. So I definitely agree with that, and that is something that we have in the pipeline to be developed in consult with the hydrogeologists. Of course, if we can leverage yourself and Anne's expertise, that would be great. But we do have a lot going on, and we're trying to make best use of investment in terms of purchasing equipment.
It's a process. We see it here in Florida. That's where Phil and I are reporting from, and it's a process to do that infilling, the gap filling, the budgeting for construction of really key components, or buying the proper equipment that will help to give you additional information so that you're making good, solid choices, especially when you've had in the Toledo district so many wells that were that fell short. You definitely want to make sure that your money's going to the right thing, because you've got it supported by the data. So that is, it sounds like you've got a lot hopping. We were curious. We've got this next webinar, and I know that you do have, we try to keep as much in tabs, from the things that we've read, that you're making some great progress in investing in groundwater, and trying to figure out what tools are available and affordable and implementable. As we get into this next webinar, does anyone have any input about things that they would like to see in particular that you'd like us to emphasize? I suspect that because you have have experienced drillers on staff, it will be very, I think it will be a compelling, useful webinar the way that we have it outlined. But if you have any thoughts, after this, and you want to share them with us, we'd really be very happy to hear about that. I guess the last one, we've got about 8 minutes left. You talked about kind of the pinch points, including the Toledo area. Are there other things that are high priority items for the hydrology unit, as well as other units within the governance? What's the most pressing thing? I know it's wet season and flooding is a thing. I'm asking kind of a broad question. What are your priorities, knowing that one of your priorities is flooding? So can you talk a little bit about your priorities and how you're addressing them?
Okay, our priorities for hydrology during this time is predominantly surface water, as I mentioned before. We have our flood early warning systems that we need to get in place. We have our national monitoring network, which we need to densify and use advanced technology to assist us in terms of real-time data transmission. With groundwater, we are starting up, but we still do have some priorities as it relates to that. One being that we need to establish a groundwater monitoring network in the north. And I mean, this is national, but we're starting with the north, in the same area that you're providing information on webinars. So any input into designing, how do we go about designing a network, choosing well locations, the factors that we need to consider along those lines. What we have completed was a baseline well survey, and we took static water level readings, but that was just a 1 point type of exercise. What would a monitoring program entail for groundwater monitoring systems? I know I briefly dialogued informally with other counterparts, and there's a challenge with well drillers being able to identify the different formations, maybe how to catalog those, to take the well log samples, documentation in that regard. How would you pull out a well log? How would you interpret a well log? These I have gathered over various conversations that these are the areas for groundwater that would be most helpful in the very preliminary phase.
Yeah, that's always a challenge when you have, drillers are so good at the things they do. They're good at the mechanical parts of it, but they're not hydrogeologists. They're not scientists necessarily. They learn a lot, they absorb a lot, and they do quite a bit of self-training. But I could see where that could be very complicated when you have very complex geology. It'd be a big challenge.
Yes, and Tennille, I was curious when I heard you mention just now interpretation of well logs. Was that the litho logs, or was that geophysical logs? Because there is downhole, borehole geophysical logging as well. That's very useful.
Yeah, I believe it's the litho logs. While they're drilling, you compile your well logs, but when you submit the well logs, what does that mean to me? So there's a need to be able to understand, not just documenting or cataloging, but understand why you're doing that, and what accuracy means or translate for other persons who would be using this information. Because for us, and you guys will know more than I do, it's very important to have our well logs, to have that stratigraphy for interpolation for vast areas or points of interest. So it's along those lines, not just collecting it, but understanding the reasons and the importance of why you need to collect it and document it properly.
Great, thank you. And as I'm sure you may be able to hear, my mowers have finally shown up, but thankfully they waited until we were at least into our question stage. Yeah, you're exactly on target with that, Tennille. I think that information is very important for doing correlations and being able to understand, how the formations may link up and what's on top of what and all those kind of things, because it can get very complex, especially up, for instance, in the Maya Mountains, for example. Much different than the Yucatan Aquifer.
Tennille, I wonder if we could do a little research and just see. I haven't looked into that, but I imagine that there may be some generalized driller guidance documents that maybe we could send through Elizabeth that might be useful to you in kind of a general way, just to, as you say, help drillers to understand why they're doing the things that they're doing and what they're seeing and why that's important. So we'll take a look and see what we can find.
Yeah, that's no problem at all. Just for context, so that you guys don't belabor the process too much, there aren't any well drilling guidelines established in Belize. So our previous experience through the U.S. Embassy's technical cooperation, we had Mr. Terry Watkins actually come down and I believe did a 1 week session with well drillers. Unfortunately, I was not there, but the reviews that I got, it was very interesting. But on our end with the administrative or the regulatory aspect, there is a need to define what those guidelines would be, so it would prove beneficial to us in any event.
Well, it's always good to not have to reinvent the wheel. If you had a base document to refine in country, that way you can tailor it to your specific your specific region, and maybe that's useful. So we'll see what we can come up with and send it your way.
Great, thanks.
All right, well, at this point, I see we're 1 minute before the hour, so I think we can go ahead and wrap up unless anyone has any last burning questions that you can feel free to add into the chat. For everyone's awareness, the third session of this webinar series is now scheduled for August 17th at the same time, and it's another 2-hour session. We hope to see many of you there. If you need an invite, please feel free to reach out to me directly, or follow up with Neil, who I'm sure will be able to provide you the invite. We are really excited about the third session, which we think will draw a lot of this theory into practice and really hopefully be really actionable and exciting for you all, and we hope to see you there. In the meantime, again, we'll be sending out these slides and the recording will be available up on YouTube, and you can feel free to send any questions you may have our way as well. Thank you for your participation and for all of the effort you guys took to be able to join us today. We really appreciated it.
Thank you all. Appreciate it.
Thank you guys too. Have a great day. Well, remainder of the day.
Thanks.
Thanks a lot.
Okay, bye-bye.
Bye-bye.
Bye, everyone.